Females are more interested in peace. Males are more interested in justice. For 22 years Stanford students are more interested in depression than sex. Two skulls, if you're an osteologist you can differentiate between female or male. How heavy, large the body was. Diseases. Malnutrition. Given birth, a lot of times or a few. Bipedal. With the right tools, you can see two skulls. And know that information. You can even figure out who's more likely to cheat on the other. Levels of aggression. Female tend to have twins, or one kid at a time. Females choose males because they have good parenting skills. Or because they're big, hunky. Live the same length of time. Same life expectancy. All, merely by applying a certain piece of logic. There's an inevitable logic about how organisms function. How organisms are built. How organisms have evolved solving problem of optimizing the solution. The tools that you can apply to thinking about evolution of behavior. Figuring out the optimal solution to behavior. Reaching the Nash equilibrium. The same sort of process of figuring out what are the rules of optimizing tic-tac-toe behavior. Can be built upon the principle of evolution of optimized social behavior. Known as sociobiology 1970s. Evolutionary psychology 1980s. You cannot understand behavior, and internal psychological states, outside the content of evolution. Darwin did not discover evolution. He came up with the notion of a mechanism for evolution, natural selection. Alfred Wallace as well, natural selection. But he has gotten screwed historically and Darwin gets more attention. First, there's evolution. Traits in populations change over time. Can change enough, that you will get speciation, new species will form. Built in logical steps. 1. There are traits that are heritable, one generation to the next, genetic traits, it's not correct to say that. 2. Variability among those traits, different ways in which these traits can occur, and they're all heritable. 3. Some versions of those traits are more adaptive than others, some work better for you, will carry more fitness, adaptiveness than others. This is not about survival of the most adapted, it's about reproduction. It's about the number of copies of genes you leave in the next generation. You've got to have traits heritable. Variability in them. Some are more adaptive, more likely that that organism passes on copies of its genes into the next generation. So, you will get evolution in population. Changing frequencies of traits. And when you throw in one additional piece, every now and then, the possibility to have a random introduction of a new type of trait in there, a mutation. From that, you can get actual large changes in what a population looks like. Everything with physiology, anatomy can evolution. So, how do you apply it to behavior? You do that the exact same thing. Behaviors are heritable, types, traits, classes of behaviors. Certain degree of variation among individuals. Some are more adaptive than others. The more adaptive will become more commonplace. And every now and then you can have mutations that introduce new variability. We will focus on certain behaviors are heritable, have genetic components. How genetic behavior is. How apply these Darwinian principles. Before we start, a caveat. Animals don't plan, don't have conscious, not take classes. What this organism want to do is just a shorthand for something sculpted by the exigencies of evolution and reducing the optimal. Applying Darwinian principles to behavior. First, unlearn something. Here's the scenario. You're watching a wildlife documentary. On the savannah. Lions on top of some big old dead thing, a buffalo. They're chewing away and having a fine time. So, they have to deal with how they divvy up the food. Another example. Migration of zebras. Following a cyclical pattern of rains. Going where the grass is greener. But the problem. There's a river in between them and the next field. A river teeming with crocodiles. So, what are the zebras going to do? The documentaries would say. A zebra will sacrifice himself so the rest of their species can survive. Because animals behave for the good of the species. Wynne Edwards. The notion that animals behave for the good of species, group selection. This isn't the case at all. Animals behave for passing on as many copies of their genes as possible. So, animals behave in order to maximize the number of copies of genes they leave in the next generation. Not survival of the fittest, reproduction of the fittest. So, if you watch these things enough, and not just the 3 minutes the program shows, you'll realize that the sacrifice is not fighting his way through the crowd. This guy is being pushed from behind. Because all the other ones are saying, yeah, go the old guy on the river. He's getting pushed in by everybody else. He's not sacrificing himself for the good of the species. He just gets pushed in because he's the old, weak guy. By the 70s as a replacement came You see three ways in which this could occur. 1. Individual selection. Sometimes, the behavior of an animal is meant to optimize the number of copies of its genes that it leaves in the next generation, by itself reproducing. Natural selection is processes bringing about an organism who's more adaptive. 2. Sexual selection, selecting for traits that have no value in terms of survival, traits that carry no adaptive value, but for some random, bizarre reason, the opposite sex likes folks who look this way, so they get to leave more copies of their genes. As long as individuals prefer to mate with individuals with arbitrary traits, those traits will also become more common. And the most straightforward way is to behave in a way to maximize the number of times you reproduce yourself. Another way of accomplishing this, one of the things that can be relied upon in life, is that you're related to your relatives. What you get is the more closely related you are, the more genes you share in common with them. Identical twins share 100% of their genes. Full siblings 50%. Half siblings 25%. So, the closer a relative is to you, the more genes they share in common with you. So, you got this issue. You're an identical twin. Your identical sibling has the same genes that you do. Individual selection. You will be just as successful as passing on copies of your genes if you forego reproducing to make it possible for your identical twin to do so. Because on the level of sheer numbers of copies of genes, they're equivalent. And sometimes, you'll thus get behavior which decreases the reproductive success of an individual, in order to enhance the success of a relative. But you've got a constraint there. All your relatives don't share all your genes with you, differing degrees of relatedness. Haldane. I lay down my life for 2 brothers or 8 cousins. That's the math of relatedness. Evolution selects for organisms coopering with their relatives. First block, individual selection, passing on copies of your own genes as a way to maximize future success. Second, helping out relatives, increasing their reproductive success, 1 identical twin, 2 full siblings, 8 cousins, as a function of degree of relatedness. Animal behavior of animals being obsessed with kinship. Animals cooperate with relatives depending on how closely related they are. Kin selection. Inclusive fitness. Seyfarth and Cheney. Vervet monkeys. They have recordings of various vocalizations from the monkeys. Like when they were angry, alarmed, etc. They reproduced a recording of a monkey infant giving an alarm call, hide it in a bush. So, the mother recognized the sounds of his infant, she gets agitated and looks over the bush. So, do everyone else in that group. They understand kin selection. They all look at the mother. What is she going to do next? They understand the relatedness. Another example. You've got 2 females. Each has a kid. One day, female A does something rotten to female B. Later that day, the child of female B is more likely to do something rotten to the child of female A. They keep track of revenge, but not revenge on the individual who did something miserable to you, but displaced by 1 degree of reproduction. Keeping track of kinship. They don't want to figure out who are their relatives. Evolution has sculpted an ability to optimize behavior of relatedness. How sexual selection play out in this realm? I'm willing to expend great amounts of energy to convince people that my siblings is incredibly hot. That's inclusive fitness. Decreasing your own reproductive potential. In order to increase the reproductive success of relatives, the more closely related. In shorten. Individual selection. None of this for the good of the species. Maximizing the number of your copies of your own genes. But, you yourself maximizing reproduction. And kin selection. Using your own reproductive potential for going to help relatives as a function of degree of relatedness. Third block. Animals forego competition at certain point. Rock paper scissors scenario. You've got animal A, B, C. A has a means of damaging B, but it costs. B has means of damaging C, but it costs. C has a means of damaging A. You get the right distribution of individuals with one of those traits, and you will reach a RPS equilibrium, where nobody's doing anything rotten to each other. E.g. Brandan Bohannon. Studying a bacterium. Showing a RPS circumstance. 3 versions of this bacteria. 1 generate a poison, but it cost, generating that poison and protecting itself from that poison. 2 vulnerable to the poison, she had a transporter on its membrane, where he could take that poison, the advantage, that transporter took up more food. 3 didn't have poison, it didn't have to spend energy on a poison, and it didn't have that transporter. So, each one has a strength, vulnerability. You get equilibrium. This was the evolution of stalemates, not in chimps or cetaceans, but in bacteria. Bacterial behavior. Behavior of all species are subject to these same rules. On passing copies of your genes. These three bacterias are competing with each other. None are behaving for the good of the species. That's not real cooperation. Merely everybody realizing. We have to cut back on the competition, aggression. Because every time I damage whoever, I am more vulnerable in another realm. But sometimes, they actually cooperate. And you see they're not relatives. Altruistic behavior. Because many hands make the tasks lighter. Cooperation can have synergistic benefits. Like cooperative hunters. Mark Hauser. Rhesus monkey. In a cage. They could have access to food. If they share it with another monkey. In other. Requires two monkeys to get the food in there. It showed clear-cut reciprocity. Monkeys who shared with another were more likely to get shared back. And got more cooperation in the situation of two monkeys. Cooperation has a strong evolutionary payoff. Even among non-relatives. With a condition. You're not putting more into it than you're getting. Reciprocal altruism. They've got to be social, smart. Because they need to remember, recognize individuals, long life. Long-lived social vertebrates. Or bacterias, like fungi. They create a fruiting body. Divided in two. The stalk attaches to something or other. And the part of fruits. So, you want to be in the fruiting part. That's the part that reproduces. And the stalk is doing all the work. And you see, is attempts at cheating. One of the strains, trying to disproportionately wind up in the fruiting part. And the next time, the other strain, will not cooperate with it. Will not form a social colony. But not just reciprocal cooperation with a non-relative. But also, whenever possible, to cheat. To take advantage of the other individual. We're more attuned to pick up cheating. Better catching up cheating than spontaneous altruism. So, what's the optimal strategy for a social species? When do you cooperate, and when cheat? Game theory. Games that have mathematically optimal strategies, multi-equilibrium. Ends up in prisoner's dilemma. Two prisoners. Both escapes. But captured. Four outcomes. Both cooperate. Both cheats. A cooperates, B cheats. B cooperate, A cheats. Highest payoff. 1 you cheat and he cooperate. 2 both cooperate. 3 both cheats. 4 he cheats and you cooperate. But what you really see in this game theory is there's anything but that going on. E.g. people playing prisoner's game. They have a brain scanner. Looking at a part of the brain that has to do with pleasure. Where some individuals activate that part when they have successfully cheated. Or when both cooperated. And there's a big gender difference. How do you optimize prisoner's game? 1970 Robert Axelrod. He programmed a video game. Where 2 players program each one's strategy. He runs a round-robin tournament. Every strategy is paired against every other strategy. And the most optimal strategy was tit for tat. You start off cooperating in the first round. If the other cooperated, you cooperate in the next round. But as soon as the other cheats, you cheat the next time. If he goes back to cooperating, you go back to cooperate as well. So, always cooperate. Tit for tat always drove the other strategies into extinction. It's nice. Retaliates if you do something crummy to it. It's forgiving if you go back to cooperating. It's clear-cut in its play. Imagine you play 3 rounds of tit for tat. R1, both cooperate. R2, both cooperate. R3, you cooperate and he cheat. You can't get back at them. Because it's the last round. So, under some circumstances, it's disadvantageous. But tit for tat may lose the battles, but it wins all the wars. Being nice, retaliatory, forgiving and clear in the rules drives all the other strategies into extinction. Summary. First building block of optimizing the evolution of behavior. You don't behave for the good of species. Individual selection, passing as many copies of your genes. Sometimes a chicken is an egg's way of making another egg. Second building block, kin selection. Sometimes passing your genes is by helping relatives. With the degree of relatedness driving it. Third, most advantageous, is to cooperate, even with non-relatives. But it has to be reciprocal, cheat when possible, on guard against cheaters. And prisoner's dilemma formalize optimal strategies for that. However, there's a vulnerability on tit for tat. What if there's the possibility of a mistake being made? Of sending the wrong signal? If someone does a cooperative behavior, but thanks to a glitch in the system, it read as having been defection. Who cooperated? But the message got through as cheating. So, he will cheat on the next round. So, the first one cheats. And so, on. 1-2 1-2. 2-1 2-1. So, you get a seesaw pattern for the rest of time. You've just wiped out 50% of the cooperation. Tit-for-tat strategies are vulnerable to signal error. E.g. USA, by accident, launched a nuclear weapon. The missile went off and destroyed Moscow. So, thanks to a signal error, a cheating signal was accidentally sent off. So, a tit-for-tat response. In order to avoid thermonuclear wasteland, the USSR was allowed to destroy New York. So, another strategy came to the forefront. Forgiving tit-for-tat. Exactly the same. But if there's a signal error, and you've gotten caught in a seesaw, we will have a rule. If we seesaw 5 times in a row, both will forego cheating the next time. But forgiving tit-for-tat is vulnerable to exploitation. Playing against players that don't have forgiveness in them. So, a better strategy. Trust. Daniel Ellsberg, 1970. Worked in the Pentagon. He stole thousands of secret files. Gave it to the NYT. About the corrupted reasons on Vietnam War. But as the beginning he was a game theorist. The optimal benefits of perceived madness. When to say you have madness. And when to cooperate. And then a zoologist. He went in the wild and saw. If were there any examples where this happened. 1. Vampire bats. When they suck blood, they are not drinking the blood. They're filling his throat sac. To disgorge the blood to his babies. So, they have a system of reciprocal altruism. Where a bunch of females will share the same nest. These are not related. Just kin selection. So, she disgorges the blood and feeds everybody's babies. A state of stable cooperation. But, if one female is cheating, and the rest of females realize, they won't feed the baby of the cheater. 2. Stickleback fish. You have one fish. You make him believe he's being attacked by another fish. By putting a mirror. So, he fights against himself. Then, make him think he has a cooperative partner. Put in a second mirror that's perpendicular. In a way he sees his reflection like helping him. And now, make him believe that his cooperative partner is cheating on him. The next time you set up this scenario, there's a chance the first stickleback doesn't attack its own reflection. He tit-for-tat, against the cheater. 3 fish species that can change sex. Black hamlet fish. 2 fish. Opposite genders. They go back and forth on gender. But there's an inequity. The price of reproduction is greater for the female than for the male. Whoever's the female in any given round is the one who's paying more. If you get one fish cheating, being more times male, the other fish stops cooperating with him. And when you look at this realm, it applying the same notion of selective optimization for behavior. When to cheat/cooperate. This sculpts something so optimized. But there were exceptions. 1. Craig Packer. Prides of lions, a bunch of relatives. But sometimes, prides of non-relatives, nonetheless, they've reciprocal altruistic. In the reciprocal system, sometimes there'll be one scaredy cat lion. Who stayed behind the others. Who wasn't punished for it. They don't use tit-for-tat. So, you have the real world. Maybe this individual is doing very reciprocal stuff. Forgiving altruistic stuff in other realm of behavior. Maybe, he eats less food. This is a world in which it's not just 2 individuals optimizing. You begin to get real-world complicities. 2. Naked mole rat. Live in big cooperative colonies underground, 1970s. And, there would be 1 or 2 animals that weren't doing any work. They were much bigger, and scarfing up food. When the rainy season comes, these big rats go up and turn around to plug the entry to the tunnels. We have role diversification. 3. Holland. The possibility of a strategy suddenly changing. Mutation. How often they were adaptive, spread throughout the strategy of individuals playing. How often they drove other strategies into extinction, when these systems are modeling the same thing. Reciprocal altruism. Natural selection, cooperative hunting, if they're not relatives. Now we have 3 building blocks. It's not survival of the fittest. It's not behaving for the good of the species. It's not behaving for the good of the good. Instead, these 3 building blocks. The ways to optimize as many copies of your genes in the next generation as possible. 1. Individual selection, me. 2. Inclusive fitness, kin selection, relatives. 3. Reciprocal altruism, cheat vs cooperates, games to optimize it, tit for tat, multiple roles. Back to the skulls. 1 males being a lot bigger than females, vs. 2 both being the same size. More male aggression, 1. Male reproductive success. What females want, 1 big, 2 parental/competent. Lifespan, 1. Male parental behavior, 2. Twinning, 2. Abandonment, 2. Morphism, shapes of things. Sexual dimorphism, big difference in body size. What female want to know when she's considering mating a male? Parental. Competent. Prove that he can provide for the kids. Males that are able to successfully forage. Appearance. In order to pass on as many copies of genes as possible. 1 tournament species. Big, bright plumage, sign of health. Twice as size. Reproduction decided by male-male aggression. Producing massive amounts of variability, in reproductive success. Selected by having big bodies. Shortest lifespan. Not using energy on parental behavior. Don't want to have twins. And don't want to bail out on the kids. 5% of the guys accounting for 95% of the matings. vs. 2 pair bonding species. A monogamous species. Both have equivalent investment. Can't differentiate which one is the female or male. Can't tell by seeing how long they live. How much they're taking care of the kids. Or in terms of reproductive variability. To Maurice, always twins. Higher rate of cuckoldry of abandoning the kids. Males take as much care of the kids. Low levels of aggression. Same body size. Same lifespan. All males have low degree of variability. Because, if you have 47 children, you'll need to take care of them. The wiring is such that you need to bonding with the offspring, taking care of them. All the males reproduce once or twice. At the starting point. By having 2 skulls. You can tell if they're bipedal, diseased or malnourished. By applying these principles of individual selection, reciprocity. And you already know all about their social system. As humans, we are between the two. Sexual dimorphism, middle. Variability, middle. Choice, I'm not going near that one. Lifespan, middle. Some genetics of a monogamous species and tournament species look like, and we're right in the middle. All middle. Anthropology supports that. Most people are in monogamous relationships. In a culture that demands monogamy. Traditionally most cultures allowed polygamy. But the majority were pair-bonded and monogamous. You get 2 versions of polygamy in different social systems of humans. 1 economic polygamy. You're sitting around, and the wealthiest guy can have the largest number of wives. An enormous skew in reproductive success. Driven by economics. 2 demographic polygamy. Like, you have a warrior class. 10 years as warrior. At that point they're like 25. And they marry someone who's 13. You've got a problem. Because a lot of those guys have been killed over the course of 10 years. Of being involved in high levels of aggression. And 10 more years of life expectancy to catch up with you. There's a shortage of males. So, most cultures traditionally allowed polygamy, before the missionaries got them. Nonetheless, within most polygamous cultures, the majority were monogamy.